All right, we are recording, Bob, and
Yep.
I'm gonna let people in.
Okay, go ahead and let people in. We'll give them about a minute here and then we'll go get started. So I had to turn my ceiling fan on. You're at 19 participants there, Corey. At least that's what my counter says. 20. Okay.
Yeah, we got two more in the waiting room jumping in,
I'll,
but
I'll give it till 2 minutes after the top of the hour and then I'll jump in.
that makes sense.
Well, good afternoon, everybody. While we wait for the waiting room to be people moved into the presentation here. Uh, Most of you probably know who I am. I'm Dr. Robert Miller. I coordinate the ALP program for laboratory proficiency testing. And I've done numbers of webinars for the Alta group, and I've been working with the FRST group since about 2020, trying to help them, have some realization what happens in the industry and soil testing and that, and try to keep up to speed with what's happening in the academic community as well. So I guess that finishes my introduction. I'm going to jump into my presentation here, talking about the First Line pilot project, and I'll kind of go into some background on that initially. Oops, that doesn't seem to work. Let's see, there we go. Guess it's going to be a click of the mouse. So one of the things I've done over the years is take a look at amount of acid soils across the country. And I did a presentation at the ASA meetings back in 2018. I put together this graph. And basically, I targeted 5 locations around the U.S., starting in the Northeast, the Southeast, the center of the country, California, and the Pacific Northwest. And these are pH distributions by frequency plots for each one of these areas for labs, for these labs, particular labs who did this soil testing in 2018. And I'm not going to tell you about how many samples are in the pool, but they're in the tens of thousands in each one of these laboratories, okay? But what you'll notice is if you go to Indiana here, you see, probably about, second, I've got to move my bar here. There we go. About 20 to 25% of the samples are below a pH of 6. You look down in the southeast of North Carolina, you're well over 50%. You look at even in Kansas, there's a bimodal distribution there, and you have basically almost a quarter of the samples are again below 6. California, much less. It's more of an alkaline state due to the lack of rainfall, but again, almost 15, a little over 15%. And finally, Pacific Northwest, again, a bimodal distribution, but again, 40% of the samples are coming in with a pH below 6. And it just tries to show you that soil acidity is a pretty broad thing across the country. People don't really think that the West has acidity issues, but truly there are places in the West that have considerable soil acidity. So if we look across the country and we look at the numerous 9 methods for measuring reserve acidity, i.e. buffer pH, and between Adams-Evans and SMP, they're the oldest methods that we use. And dominantly, the SMP came out of the Midwest, the Adams-Evans is mainly off the East Coast. And then we have the Mehlich buffer that came out of the Southeast. And you'll see here across the country, we've went through an evolution in the last 20 years where we went from the standard SMP, the standard Mehlich buffer, the standard Adams-Evans, and now we have these modifications. And these modifications came online to try to get rid of the hazardous reagents that are within these different buffers, with the idea that you do a buffer pH to measure the amount of reserve acidity. And so we have quite a plethora of methods of doing buffer pH or calculating the amount of acidity to figure out how much lime has to be applied. And it's really quite interesting here. These are pretty much on regional basis here. I mean, the Woodruff is kind of out of Missouri. The calcium hydroxide is a recently new one that came out of Georgia about 15 years ago. So you see how these have all evolved kind of on a location, and then they went through a modification to adjust for the chemistries of the reagents. And if we take a look at this data, we have about 31 land-grant universities who have developed Lyme recommendations for the individual states across the country. In some cases, these have been merged across a couple states, but in essence, they're all on a particular state where this research was done probably 30 to 50 years ago. And one of the things that I brought to the first group back in 2021 was I had great concerns about, well, if I go across a state line, do I get the same Lyme recommendation? Being that I'm probably seeing a different buffer being used and a different calibration data set on that. So I did this study in 2022 where we pulled 6 soils out of the ALP database. You see the soil IDs there, and I've ranked these by water pHs. So we had a very acid soil in that 2113 there, and we go up to about 5.8 there on 2115. And then there's right next to it is the Socorro buffer pH, and you can see all these would have some type of Lyme recommendation to it. We took this data, we gave the labs here, it says, here's your water pH, your salt pH, here's your buffer pH. I says, give us a Lyme rec based on a 6-inch depth. And we're going to have a target finish pH there at 6.5, and we're going to assume 100% calcium carbonate. We didn't want to go through any kind of ramifications. Well, one state uses 80%, another state uses 75, etc. And so the bottom line was that these are soils collected across the country. These have clay contents that range from 7 to 31%. So it kind of represents a broad range of textures. And I'm only going to show you data for one of the 6 soils, but this is pretty indicative of what we found in that survey. And that was when we asked them to provide Lyme recommendations for the 31 states that participated in this. Oh my gosh, yes, there's a median value there about 3,000 pounds, 3,300 pounds of Lyme, but the numbers range from 7,000 down into a few hundred pounds of Lyme. And so this was quite disturbing to me in that, we think these Lyme recommendations are pretty solid, but when we have this kind of variation across all these land-grant universities, this is quite troubling. It really kind of tugs at our credibility as a group of agronomists. So 900 to 7,000 pounds is that range again. So I met with the first group, and we've discussed this many times, and John Jones jumped in on this with us, and we tried to say, well, why are these differences? Well, the bottom line is that there's multiple buffer pH methods here, and that the initial calibration research for doing the incubations is quite sporadic. And what I mean by that is some people run 30-day calibrations for incubations, and some people do 6-day, 2 months. And then there's older literature out there that are 6 months. And so you have all these variations in how the research was done and how what buffers they used. And it really became quite interesting. How come it's not surprising we had this kind of issues. John Jones and a group of us just published a publication of that. That's in the October edition of Triple SAJ. You can take a look at the research of all this data that we did in the survey. I think it's a really foundational paper in terms of saying, okay, this is where we are as an industry, and these are the issues that we have. So, so I don't know how many in the call here of 26 people that are online right now, but many of you are familiar with the first group, the Fertilizer Recommendation Support Tool. And its whole idea is to promote clear, conscious soil testing interpretations for making fertilizer recommendations. It's comprised primarily of university and government researchers across the US. There are a few industry involved, and has mainly focused on P and K soil testing and calibration recommendations. And if any of you online who have never been to the website, I urge you to go there, because it's one of the most informative websites I've ever seen on soil fertility, at least in North America. So in 2021, we initiated a project to conduct a national research project focused on lime recommendations based on what we found in this survey. And the whole objective is to develop new lime recommendations across multiple buffer methods. Very few people have done research where they compared multiple different buffers on a set of soils data. I'm only aware that Oregon State recently published, I think in the last 4 years, one where they compared, say, the SMP, the Socorro, and the Malick buffers all side by side. It was quite a task getting this undertaken because everybody said, well, acidity is different in North Carolina than acidity is in the upper Midwest. Well, truly, acidity is acidity, independent of soil type and it's dynamic. It changes with the production practices than anything else. So I made the proposal that we collect 120 soils across the US and we try to capture soils from all the major physiographic regions of the US, but with focusing on the major 4 regions, the soil work group regions. And I wanted to make sure that we kind of took a big survey of all these parameters, and in that pH runs from 4 to 6.4. And we cover textures, we cover a wide range of CEC, soil organic matter, and a wide range of mineralogies. I've got quite a group here of people that work on this project. I'm not going to go into all the different names, but you can see we cover the country in terms of all the land-grant universities here. And it really focuses on people who have a working knowledge, working in soil acidity. I think I won't make one point here. David Kissel, retired from the University of Georgia, spent the last 20 years of his career working on soil acidity in Georgia. And he's kind of our go-to guy to talk about what happened in the past and why things were done in that matter. Our project team, we really want to focus on covering the analysis scheme, the experimental design, and a QC protocol of how we're going to do this major lime incubation research. Okay, as of today, we've collected 146 soils representing 40 states, and the textures range from a loamy sand to a clay loam. I think we've got that captured in terms of that. At each one of these sites, an individual went to the field, collected 15 to 20 pounds of soil. We required that they collect metadata on GPS, depth, moisture, crop, tillage, a whole wide array of data that's associated with pulling that sample. It was quite a feat trying to tell people, well, you know, if you're going to use a 3/4 inch probe, you're going to have to pull 200 pokes to get 20 pounds of soil, you know. But this has all been accomplished. Soils were brought to Colorado. We dried, we sieved, we homogenized all these materials, and then we took those down to the University of Arkansas in 2 shipments, one in April and one in July for the incubation study. Preliminary wise, we analyzed these soils for water pH, salt pH, modified Malick buffer, Malick 3 cations and fertility package, organic matter by LOI, and texture. So the whole idea was, let's capture some information on this soil. This is by no means all the analysis that we're going to do on these, but this is the preliminary analysis we did on these soils. Now, this is a map, GPS locations. You can see here all the different locations that we pulled these from. I'm sorry, they're in the lower left-hand corner. The color codes for the textures didn't quite come through. That's my area. But you can see we've got soils from the West Coast. We've covered the Southeast. We've got quite a collection in the Nebraska, Iowa, Illinois area, and then a really good representation out of the Pacific Northeast, out of Vermont, New Hampshire, and Connecticut. So it's truly, you know, countrywide. You'll see one soil there located in south central Colorado. That was the only acid soil I could find in the state, and I thought it was behooved me not to at least have at least one soil in that data set from Colorado. And it's not shown on here, but we actually have a soil from Alaska in the data set. So if we took a look at the data, and this is just 4 parameters here I'm showing you. This is water pH, modified Malick buffer, organic matter, soil organic matter by LOI, and Malick 3. And I've just given you population stats to what these population of these soils look like. So we nailed the low pH, again, pH of 4. First quartile is 5.16, which means 25% of the soils are below a 5.16. 25% of the soils have a Mehlich modified buffer value of below 5.9, which is quite remarkable. I did not know we would have so many severely acid soils in this data set, but I think all our colleagues who went out there and collected these soils and found them. You can see their organic matter. We cover the gamut from 0.2% to 12. And look at calcium, Mehlich 3 calcium. The range is from 108 out to almost 5,100 parts per million. I think we have a good data set here in terms of saying, okay, we captured quite a pool of samples to do incubation studies to study lime reactions. As I said, most of the early research on doing incubations was 30 to 60 days. Some of them earlier, prior to the 1960s, were 6 months. But there's a problem when we wet soils with lime and we incubate them at room temperature for a long period of time. And that is, some of these soils are going to facilitate nitrification. And what happens is that as ammonium goes to nitrate, we're releasing a bunch of protons, and it's going to bias down the reaction of the lime. In other words, it's going to chew up some of that lime in the process of nitrification. And we wanted to stay away from that as much as possible. And one of the other things I didn't put in this slide, but the problem is calcium carbonate does not react really fast. The solubility of calcium carbonate, I think, is like 0.17 milligrams per liter. It's almost insoluble. So you have to go through the process where some of the acidity is neutralized, and then you have to wait for the reaction to proceed to bring out the rest of that calcium carbonate into solution. So our pilot study really was to focus on 2 lime sources, lime rates, and that incubation period. So our first team on the lime incubation project really got together, and we hammered out this idea of a pilot study. We didn't want to jump into all 140 some soils all at the same time. We wanted to perfect the laboratory process for doing the incubations. So we selected 3 soils from the ALP archive. They ranged from 4.1 to 5.3 water pH. These were a sandy loam, a silt loam, and a silica loam from our archive. And we have good data on these to feel that these values are very constant. We picked 2 lime sources, and there's been some published literature to recommend calcium hydroxide. It's much more soluble than calcium carbonate, so the reaction is going to go much faster, and therefore we could shorten the incubation period. And then we went with lime rates from 0 to 4 tons on these particular 3 soils of both particular lime sources. And the idea behind that is we got a check, and we've got a pretty high rate of lime. And then we went with incubation times, and we staggered these slightly. So on calcium carbonate, it's from 4 to 60 days, and on calcium hydroxide, it's from 2 to 30 days. And the reason is that the shorter time in calcium hydroxide is because it's much, much faster reacting. So now, just to give you a quick background on these soil properties of these soils used, again, 4.05 there on the loamy sand texture, the sandy loam texture, 5.12 on the loam texture, and that HWCK, and that stands for Hanging Woman Creek, is where we collected the sample. It's at 5.33. And if you look down there along the page there, you'll see Socorro and Mehlich buffer pHs. These are all will have a significant lime recommendation going out on them. Organic matter really covers from about 1.3 to about over mid-5 percentile. CECs, this is the thing that I like to focus on, because the higher your CC, the more potential acidity you have to neutralize. And so they range from 5 to almost 23. And then we did 50% water-filled pore space, because when we incubate these, we kind of wanted to make sure we incubate them in a constant moisture content. And so there you have the different values for those 3 soils. Now, each soil treatment consisted of 2,100 grams of soil. There's 12 lime source by rate treatments going on with 3 replications. When I agreed to take this on, I figured there'd be over 400 samples, but in the end, between 3 soils, 2 lime rates, 2 lime sources, 6 lime rates, multiple days of incubation, it was 855 samples. When we took on this project, I realized right away mixing the soil with the lime is really critical because for a very low lime rate, you may actually mix 1/10 of a gram of lime with 100 grams of soil. We have this cone blender that you see there at the right that we use to mix these with. We did a pilot study to the pilot study, figuring out the amount of blending time it takes to truly mix the reagents. We were satisfied that 10 minutes of blending was really effective for mixing the lime with the soil, be it calcium hydroxide or calcium carbonate. We incubated these at 24 to 26 degrees centigrade at a room humidity of 25%, and we had a data logger running all the time while these projects were on. So we made sure that we had constant data on what the temperature was. And I'll show you this next picture. This really shows you how we laid these out. These are 120 mil specimen cups. We put in 100 grams of soil, whatever the treatments were. We brought them up to 50% water-filled pore space. We have, your 5 lime rates there at the side that you see the check with the 6th lime treatment's not shown. And that's just what an 8-day incubation was. We wrap these with saran wrap to a limited degree to minimize the evaporation. And we would check every 3 to 4 days, how much water did we lose? And in essence, I don't think there was any time that we lost more than 3 or 4 mils of water to evaporation. And so bottom line is it's really, okay, let's put them in there and let's see how we can keep this so we have a uniform situation going on there across the different stages. And believe me, we started these, day 1, and then day 2, we pull off the calcium hydroxides. And then day 8, we pulled off calcium carbonate and calcium hydroxide, etc. So it's quite a staggered process to get all this done. So when we were completed, we took these soils immediately on the day of completion. We threw them in a drying oven at 50°C, dried them for 8 hours or until moisture was less than 2%. We hand ground all these with a mortar and pestle. And we sent these off to Best Test Analytical in Moses Lake for analysis. It happened to be in their off season, so it was a great time to capture a lab that wasn't busy. Our lab analysis was quite involved. We did water pH, salt pH, Socorro buffer pH, EC, KCl extractable ammonium, nitrate, aluminum, manganese. The manganese was something that the lab recommended, and then finally exchangeable calcium and water soluble calcium on a 1-to-1. I was always interested in how much the lime actually ends up in the soil solution after it's neutralized. And we've reviewed the data and prepared the data set for statistical analysis. Now, here we get into the nuts and bolts. So this graph at the left is the BR soil. This is the sandy loam. You'll see here we have the lime rates going out to 4 tons, and we have water pH on the vertical, and we have in blue dots is calcium hydroxide, and in red is calcium carbonate. And the thing that jumps off the page at you, it doesn't make any difference at 8 days what source of lime we used. Those graphs are identical until you hit the 4 ton to the acre, and then they diverge. And the reason is calcium hydroxide is much more alkaline than calcium carbonate, and therefore we're really driving the pH up into the alkalinity with the use at 4 tons to the acre of calcium hydroxide. At the right is the SGS soil. This is a loam texture soil. You can see there's a little more scatter, but it didn't make any difference. The lime rates till 2 tons to the acre overlapped one another, independent of the source of the lime. Now, how about incubation? The lime rate here for the BR soil, here we go. And then we have the SGS soil, and you have the HWCK soil. This is all crossed all incubation periods from 2 to 30 days, 3 replications each. And for calcium hydroxide, you can see on the BR soil, it really doesn't make any difference what the incubation time frame was. Those different data points overlap. When we got to the SGS soil, there's a little bit more scatter, but the relationship still continues. And then for the HWCK soil, which is the heavier of all 3 textures, a lot more scatter going on there. And I'll address that in a moment. If we look at the incubation day for the BR soil and the HWCK soil, here is, we have incubation day on the horizontal, we have pH on the vertical, and now I've segregated out the different lime rates, all 5 lime rates that you see here. So at the very bottom is what the control did. No lime added, it's static through the 30-day time frame on the BR soil. And you'll see at the very top is the 4 tons the acre, and there's a slight slope to that. In other words, is over time, going from 2 days out to 30 days, there's a slight slope to that where it's saying, well, even at this highest lime rate, there seems to be a little bit of acidification going on there, pulling stuff down. It's really more remarkable, though, if you look at the right graph, which is the HWCK soil, and you can see all different lime rates from 0 to 4 tons all have a remarkably downward slope that decreases as pH decreases through the incubation period. Now, I mentioned earlier about nitrification. It just so happens that the HWCK soil had the greatest nitrification of all 3 soils. Before I jump into that, this is some data they provided on extractable aluminum and soluble calcium. My gosh, this is textbook where we added lime, and this is all the data for the BR soil for the calcium hydroxide treatment across all incubations, and you can see that aluminum absolutely crash with the first few units of lime put on this end. And once we reached a pH in that soil of about 5.3, 5.4, we basically zeroed out the aluminum, the extractable aluminum in that soil, which again is good textbook example of neutralization of extractable aluminum. Calcium there, you see at the right, a little more noise in the data, but it works just like what we thought it was. The higher the lime rate, you neutralize the acidity, and that calcium part of it ends up in the soil solution. I made note of nitrification earlier. This is the data set for the HWCK soil. This is a half ton of the acre of lime applied for incubation periods out from 2 to 30 days. At the left is what the ammonium nitrogen concentration by KCl extraction was in these soils. And you can see it's static there for the first 8 days. And then after 8 days, it starts to drop like a rock. And by the time we get to 30 days, it's gone from about 34 part per million down to 30, which tells you there's lots of nitrification going on, and which shows up exactly in the nitrate concentrations over that same time frame for the same soil. So think about this. We took a soil that was about 15, 18 parts per million nitrate, and we made it, almost 90 parts per million nitrate by incubating it for 30 days. And the release of all that hydrogen from the nitrification process had a profound effect of lowering the pH with our lime treatments. So the bottom line is there was no difference as far as we were concerned between the pH values by either lime source. They were the same. Only when we got to the highest rates did we notice a difference, and it's the fundamental nature of how much more higher pH values of what calcium hydroxide has. Lime rate increased pH in all soils, and the least on the highest CEC soil. So it really shows up there's a textural implication there. And again, I just talked about nitrification and incubation time. I think it's something that had to be considered before we move forward with the incubation study for all 146 soils. I can tell you my gut feeling is that anytime we see organic matters over 3%, we're probably going to be dealing with significant nitrification processes, which becomes a problem for us to deal with when we start to look at this data. Real surprising to me was not so much the extractable aluminum crashing with pH, but extractable manganese. I got to tell you, I didn't show you the graph on it, but it absolutely crashed on as the pH went above 5.5. I mean, it went from 30, 40 parts per million down to almost unmeasurable once the pH got above 5.5. And one thing I did not show here, but the precision was the highest for the calcium chloride extraction, the salt measurement. It was phenomenally about 50%, had a RSDs 50% of what they were with water. Now, before I I showed this data to the first group and we got into the mechanics of this measuring the incubation. And a subject which many of you that work in soil testing labs may find it's kind of glossed over. We don't pay much attention to it, but we need to. And that is when we scoop soils, we're scooping a assumed scoop mass, and then we have the confluence of weighing. And so when we got launched into the incubation study, we started having discussions along, well, should we do all this data work on water pH scooped mass, or should we do it on actually weighed samples? So I asked the North Carolina Department of Agriculture, David Hardy and Don Edlin, about doing a quick study for us. Let's compare scoop mass against weighed mass. On in particular, we did two soils, but I'm only going to show you the one here, 2504. 2504 is a sandy loam texture. It has a very high density. When you scoop it with a 2-gram scoop, you do not end up with 2 grams. You're at about 2.6 grams, so it scoops heavy, okay? And we asked North Carolina Department of Ag, let's weigh these out from 6 grams to 16 grams and across this incremental range that you see here. And said, do salt pH and do water pH. And so the graph at the right is this particular data generated by NCDA. The bottom line is here that you'll notice that the water pH drops significantly as we go from a low mass to a high mass. And those two arrow bars you see there, the one at the far right represents what that scoop mass actually is. It's a 15.1 gram when you're putting in using a 10-gram scoop, okay? But if you weighed it, you'd be back there at the 10 point. And so you see a significant drifting down in the pH. Whereas when we use a salt pH, it's pretty static. There's a slight slope to that, but it's pretty minimal. I'd say it's probably well within the measurement error range. And why is this? Well, when you scoop a soil, the salts that in that soil form electrical conductivity for that junction, for those electrodes. And the higher the salt content has an impingement on that pH reading. And so the more soil you weigh into that container, the more salts you're putting into it, therefore it depresses the pH. So it's fundamental to the process of using an ion selective electrode for measuring pH. And this graph really nails that home. So bottom line is the amount of salts in that soil really do affect the pH, but when we use a salt pH with 100th molar calcium chloride, we're kind of neutralizing much of that effect. So how about buffer pH? So we asked David Hardy and Don Edlin about doing the same thing for buffer pH, for the modified Mehlich buffer. So this is the same soil, and we have, again, masses ranging from 6 grams out to 16 grams. And you can see that's a pretty sharp dive in that relationship as we go to heavier and heavier masses. Again, I've indicated here what a 15.1 gram sample scooped would be, and then what it would be if it was perfectly a 10-gram mass. And there's about 1/10 of a unit depression when we use the scoop mass for the Mehlich 3 modified buffer on this particular soil. Now, if we have soils that fall around the perfect mythical 1.18 grams per cc, we're probably going to be pretty close to that 10-gram value and we'll be good. But we have soils that scoop light, like a soil that's a silty clay loam with 5 or 6% organic matter. It's going to bias it farther and farther up that graph to the left. So this is something we had to take into consideration when we're doing this massive incubation studies, and we've made a decision on that. The bottom line is we're going to do both. We're going to scoop these for mass, and we're going to weigh them both, so we have a complete data set on the pH, on the effects of lime on the buffer pH. So take a last minute here to talk about Raj Singh. Raj Singh is our project postdoc on this project. He's doing all the incubations at the University of Arkansas. It's very involved work because each incubation consists of 6 rates of calcium carbonate. We chose calcium carbonate over calcium hydroxide because we felt that it was more indicative of what's used in the real world. These are going to be incubated for 8 days at 50 to 60% water-filled pore space. We're going to do pH water, pH salt at the end of each incubation. And again, as I just said, scoop mass versus weighed. Guys, this is a lot of work. If you just do this back of the napkin math, it's over 2,700 samples that have to be run through incubations and for 8 days. We can't do these all at once. And so we've agreed that we're staggering these. We're doing one set a week and multiple sets. And I think if I remember right, and Nathan can jump in here, I think we're running 12 to 15 weeks of incubations. And we had to build a QC program to make sure that we're getting the same thing on the same soils through time. As of September 11th, hats off to Raj. He's done 60 of these incubations of last week. We hope to have this done by December, and then the work really begins on the data analysis. This is going to be a pretty unique data set because in the end, when we're all finished, we're going to have the effect of lime on water and salt pH, weighed and scooped. We're going to have this massive database on all the buffers because we're running all the buffers on all these soils. And so we're going to be able to look at buffer equations across the board. And you know, I think this data set will be able to kind of resolve us to a point to say, well, in the Southeast, buffer Y works really good. When we now have a calibration data set for the entire region for that. But buffer X works much better in the upper Midwest. We'll be able to segregate those things out because we have a database of soils for this to be used on. So with that, I'll take time for questions.
Right, Bob, I really appreciate that. A lot of information, a lot of, hey, you know, here in the next year, we're going to learn a lot more about liming. And I think that that's really important. You know, one thing from when I ran a lab days, I remember is that, or I always tell people is that lime is probably one of the #1 reasons people are soil testing to get their lime recommendation. And so it's important to get it right. And I think sometimes people are really surprised when they see the amount of variation that's out there. So I'm really excited that FRST is taking on this project. With that, I will just invite folks to, if you have questions, let's put them in the chat and we'll get Bob to answer them. So anything's up for grabs. Hopefully it's related to this presentation, but you can talk to Bob about anything, bro. I guess.
No, don't say that, Corey.
Yeah.
Well, I got to tell you, this is one of those projects. I brought this information to the first group. Deanna and I had a couple of dinners talking about this. I thought lime was as equally important as doing all the P&K work we have. It's a big dollar thing. I mean, I think the last time I read anything that there's like 3.5 million tons of lime that's sold every year in the United States. So it's a big deal.
Yeah, I think that's a good point. You know, you mentioned a big dollar thing. I'm just curious, how much is the budget for this project? Can you kind of ballpark that? It is a lot of effort.
Nathan, you're a bigger expert on this.
Yeah, I'll jump in. So the funding for the project, you know, our project overall is funded by NRCS CIG grant, and then we have matching dollars that we had to use to obtain that grant from the Arkansas Fertilizer tonnage fees, and that's what is funding Raj's postdoc. We also secured a grant from the Arkansas Fertilizer tonnage fees for $30,000 a year for the next 3 years, and that's covering our travel cost, some of the analysis that we are not getting gratis. So I mean, it's I don't know that we have a specific budget. Objectives for this study are intertwined with the NRCS grant, and then like I say, we're using the fertilizer tonnage fees to pay for Raj's postdoc and travel and analysis that's associated with it. So it's well over $100,000. And then I would also add that to characterize the 146 soils, we are asking folks that are labs that are routinely doing each one of the different buffers. If they would run the soil through their lab using their method simply because they do it on a daily basis. So, when you take the 146 soils, multiply that times 3, and I don't know what each lab typically would charge, for buffer pH and pH analysis. But all of the labs so far that we have asked are doing that gratis. So there's a lot of in-kind contributions to this project as well. And I guess I'll go ahead and plug. We are looking for really the two of the bigger buffers. We do not yet have a lab procured to run the analysis for Socorro and SMP. So if you're interested in that, reach out to us.
That's great. And so for those that don't know, that was Nathan Slayton, who is, I don't know what your title is now at Arkansas, soil expert, extreme at the University of Arkansas and president or something of FRST. So the big leader. It's sorry, I don't know your title, Nathan.
No, that's fine, Corey. I don't even know what my title is today, but I'm actually a full-time administrator in the agricultural experiment station. I've continued to run our soil testing program, and the first project is really just my passion and what I do on the weekends and the evenings. And actually, this is the fun part of the job, not so much fun doing administrative work.
I love that. There's not a lot of people that say that the soil testing part is the your passion and what you do on the weekends. So any questions for Bob? Let's put in the chat. Bob, I'll kick it off. What, so I saw a lot in this presentation of some pre-testing, some thought processes. Now that it's kind of early, I know you don't have actual data yet, but what is there anything you would have done different from the start on this thing? Is there any question that you didn't stop and answer or ask that maybe you feel like if you had unlimited money or unlimited funds you would have? I know it's kind of open-ended.
I know it's kind of open-ended. Well, I come to this a little bit different than most because I understand what the testing industry is about. I also understand the methods. And there was a lot of stuff that, over decades of running PT programs, I knew we need to do this. X and Y, we got to do this. It's one of those learning things. We did the pilot study because, well, we thought we knew what we were going to do, but we had to flush out that we really did know what we were doing. And truly, to me, the pilot study really elaborated. Guys, we don't need to do 8-day or 30-day or 60-day or 6-month incubations because, one, we had the nitrification problem, but also, if you mix the soil well with lime for a research set, now I'm not talking field work here, but a research set, you can do this. You don't need a week's really good time frame to work with. The latter graphs I showed you the effect of scooping versus weighing. This was a subject that came up after the pilot study was finished. And as Raj was getting really involved with doing the tests, the first group met as a group and we talked about, well, should we do this or do that? And I says, you got to have data. You can't make a decision without data. And so thank goodness to North Carolina Department of Ag, they were willing to run a quick study for us on that, very simple. And that was a little bit more eye-opening than I thought. I knew there would be a difference, but it was more striking on malic buffer pH than I thought it was going to be. So Corey, you asked me about things that I would throw in there if I had more funding. I mean, our goal is to develop new lime recommendations across the country based on multiple buffer methods. I do look at this in a longer term that we're going to shrink that group of 8 down to 3 or 4. Don't know that, but my guess is that's what's going to happen. I got to tell you, I have data sets I've worked with. I've done some commercial collaborations with commercial labs. I'm actually convinced we really don't even need to run buffer pH. I think we can model the acidity in the soil, but this project will now have a data set to examine that further on. The last thing I'll say, and of course, I'm always thinking about curiosities, right? One of the things I don't think we've really tackled, we've talked around the fringe on it, is what liming does to CEC. You know, CEC is a pH dependent process. And I'm got some preliminary data of my own that, sure, the soil CEC at pH 7 is 12. But if you look at that native soil under native conditions at a pH of 5, that soil CEC is actually closer to 7 or 6. And I would like to see us kind of say, okay, let's look at the acid soil before and after lime, that, you know, whatever the rate we decide it takes it to 6, 5, or 7, and say, hey, guess what happens? You know, you put on 2 tons of lime, you're going to raise your CEC. And it's something I don't think academics and a group of us are really quite ready to dive into, but I think this data set, these soils will give us that opportunity. I think it's a good way to say, hey, you know, you got acid problems in a field? Oh, that's fine. We'll put on a little lime. But guess what? Guess what happens to CEC when you lime it? It goes up. I think everybody would say that's a real plus. So anyway,
No, good response. So there is I think this is actually a really good question in the chat. Do you plan to validate lab-based incubation with field trials given nitrification does occur in real fields? So I think that's a great question, right? Because we all know when we do an incubation, we're simulating, we're not actually in the field. Maybe you can talk a little bit big picture and then, hone in on the response there, Bob.
you know, I totally agree. I mean, I have a farm. We put on lime periodically every 3 to 5 years, and yeah, absolutely, nitrification is a big deal. Uh, the other side of the coin is, you know, you pull the sample in the fall, okay, and let's say it says you need 2 tons of lime, fine, and then in March you put on 250 pounds of nitrogen, you know, it's analytical nitrogen. I got to tell you, you know, the line that you put on based on the fall recommendations, probably part of that's going to be consumed up for the nitrification that happens the following spring. I have another pet project on this whole thing is I think the first project should find grant funding in the future and come up with a model to say, well, if this is my cropping system and this is how much nitrogen fertilizer I'm putting in my system, I can predict what time in the future I need to put lime on, you know? And you can soil test to validate that. But the reason I say this is I work with several farmers. They sign long-term leases on their properties that they lease. And a couple of their landlords want to build lime into their leasing agreements. And I think this is something that is needed. So,
Corey, if I can add to what Bob said there, based on the question that was put in chat, we are trying to put together a proposal for federal USDA NIFA funding that would focus on this question, and that is to take all of the incubation trial data, assimilate it into, do we need regional recommendations or is one national framework suitable? And then to do field trials in selected states to validate and see whether or not, what we're seeing in the incubation trials is mimicking or predictive of what we see in the field. So, all of this stuff takes time. I will, just say that we are, based on the timeline that Bob gave, we're not going to be finished with the incubations in December, Bob.
okay. Well, hey, listen, I'm optimistic.
Yeah. So our lab in Arkansas, where we've been doing this at our Mariana lab, has started to get busy because we're in full swing harvest and consultants are out pulling grid samples and delivering them as we speak. So we're actually trying to figure out how to work in 1,100 samples that we have from the 60 incubated soils to get them on the pH instrument to run water pH and salt pH. It'll be sometime in the spring, probably before we have space, time, and labor to restart these soils. But I think we've got some things that we're going to be doing on the interim that I think will add to the project. So hopefully I didn't ramble on too much, but yes, we do have those plans. But it takes time and money, and hopefully we'll find both.
Nathan, that's what I love about the first program is you heard a couple things there, going to an applied setting and multiple states working together. And I think that's something we haven't seen all the time in the past. So one question just came in, Bob. We are interested in demonstrating and quantifying the yield impact of liming in New York, hay or corn silage, in addition to pH, water, and Malic 3 buffer pH. What else would you suggest we add to the measurements? Yeah, modified buffer Malic buffer pH, not Malic 3.
Well, I'll say, so I'm going to make the assumption these are field trials, right?
Go ahead and make that assumption.
Yeah, I'll make that assumption. You know, if the soils are strongly acid, and I say strongly acids below 5.6, I'd be throwing extractable aluminum on there because you want to make sure that you're going to zero that out. And I would throw in manganese. I got to tell you, that was a shot out of the dark that I was shocked to see how much the extractable manganese was going on. And I did some homework afterwards and I found out, guess what? There's a lot of old literature out there talking about manganese toxicity in the mid-Atlantic associated with very acid soils. Of course, the acidity is probably the bigger problem than the manganese. I mean, other than that, I don't see anything that you want to do. I mean, there's lots of things that you could do, but they're not going to be earth-shaking changes to what you found, right? I mean, the effect of lime. The other thing I will throw onto this is I think how they incorporate the lime's a big deal. I mean, I know people who lime fields and they throw it on and they go out with a field cultivator and that's good for mixing. Well, it's not. It don't get much effect on depth. A lot of these no-till operations I've been in where you look at the soil pH with depth, and guess what? The pH at the surface is 6.2, but at a depth of 6 inches, 4 to 6 inches, the pH is fives or 5.1s, and extractable aluminum is off the scale. So, I mean, from that standpoint for field work, those would be the two things I would probably take a look at.
I think that's good. Bob, one question I got texted to me actually. Will you go to the slide where you show increasing soil sample weight and the shift in buffer pH? As
This
farther
one?
back than yeah, that one works. So I think and I kind of agree with this person that texted me. They were saying that they think of buffer pH, and they're probably quoting me on this, as probably the most stable test in the lab. And then
Oh yeah, without a doubt.
yeah,
Without a
yeah.
doubt.
And to see this shift from almost 6.4.5, we'll call it 6.4 to almost 6.2 or something. That I mean, that's for buffer pH, that's kind of a big swing. I'm just wondering. I mean, it's not huge, I guess, but
yeah,
it is.
remember, but Corey, remember this. We're talking about a scooped mass versus an actual weighed mass, okay?
Yeah.
And what I'm trying to say with this particular graph is if your lab scoops all the time on a scoop mass, then on the coarse textured soils, you're biasing the buffer pH down. And you'll always, as long as you use a scoop mass, it's always going to be a stable test. But conversely, if you get
It's going to
into
be stable, but you're biasing it low. And
exactly,
that's the question that I got asked is if a lab is scooping and they know that they're doing a field or something that's a more coarse soil, should they be making adjustments or should they just
I'm not going to go there. I'm not, and the reason I'm not going to go there, I want to see what the data looks like from all the sandy soils versus the loamy soils versus the fine soils we have in this project, because we're going to have
not
that
ready
data.
to make some thought. Not ready to fully. We don't have enough data to fully flesh out that thought.
Well, here's my concern. Okay, So if you're scooping, and nothing wrong with scooping, people, but if think about this, I don't know the math right off the top of my head. I'm sure there's people who run modified buffer all the time and have an idea what their lime rate is. But if you look at this graph, you're probably talking at least 800 to 1,200 pounds of lime recommendation difference, right? Now remember, this is the perfect world, right? We're doing this under very controlled conditions, and we don't have all the other incidental factors coming in, about the previous crop and how much did it rain and all this. But if you think about this, if this is reality, which I do believe it is, then a fine textured soil with 7% organic matter that has a bulk density of 0.9 versus this soil that has a bulk density of about 1.6, those are wildly different numbers. And it was one of the reasons we decided that we're going to have to run scoop west. We're going to do scoop mass and weigh on everything we do for this project.
Okay. Fair enough. I got that text and I was just thinking it's an interesting question.
Well, I do agree with you that buffer pH is one of the, under a given system, be it mass or scoop, is very, very stable in the lab. And one of the reasons it is, guess what? You know what? The EC of a Mehlich buffer pH, the EC is like 8. It's got a lot of salt in it. So
excellent. Well, so I think that does take us to the top of the hour. I'm gonna thank everyone for participating in today's webinar. It was recorded and we're gonna get it shared out and it will be posted on the website as close as we can. Yes, I see Nathan's already starting the charge. Let's all give Bob a round of applause. If you know how. Zoom has updated, so I wasn't sure how to do these reactions, but
yeah, the floating hands clapping.
like it. All right. Thank you guys. Thank you, everyone.
Later. Take care, everybody. Bye.